Like this is one of the tougher A questions I've seen in any junior maths Olympiad. I mean, we don't have to show working, but obviously you should. But there's a lot to consider along the way. No, a lot of the A questions are okay, I think. But yeah, this one's a really nice arrangements question. So when I did this, I decided to first of all number the cubes. One, two, three, and four. I'm going to get onto colors in a minute, but I feel like the first thing we should think about is whether they will look the same when we rotate it, because that's what it's getting at. Like two shapes are considered to be the same if it can be picked up and turned to look identical. So I'm going to imagine picking this up and turning it around. And you're not going to have multi-link ready to do this. I mean, you might, if feel free to try it now if you're just practicing this challenge, but you got to try and do it like sort of visually or in your heads to find out other configurations. Now we can safely say that however we rotate it, the two is connected to all three of them. There's no way that that's going to end up on the end or anything. So if it's going to turn, the two is still going to be here. That's quite a nice, thing to just put that right in. So I want you to just sort of imagine this for a minute. Imagine like rotating this one up, like rotating the whole thing, I guess, clockwise, and then turning it this way. It's kind of hard to do it when it's in 2D, but basically, as I rotate it up, the one is going to end up here, and as I turn it round, the um the three is going to end up here, and the four here. That is another possible configuration just from turning. So hopefully, yes, you can see that because it is possible. And if you're not happy with that, then by all means, like put some cubes together and see that like number them, and you'll see it does work. Okay, kind of makes you think if you're happy with this one, it kind of makes you think surely there's another way you could rotate it to get three at the top. And there is, because we can basically just do exactly the same thing again. Look, just like one moved to the top, now three is going to move to the top, and then four moved to here. So now one is going to move to here, and four is going to be here. So we've got these three different configurations that are all the same, like for a given kind of setup. So once we understand that, we're pretty much, well, I say we're pretty much there. If you're happy with your arrangements, we're pretty much there. We're going to color the first one. Okay, let's say we color the first cube number one first. There's going to be four options for coloring it. And then I'm going to color number two, and I can't color it the same because we have to have all of them different. So there's going to be three options for that. This is your classic arrangement situation. You just look at the number of choices. It's the product rule of counting is another name for it. And then when I color the third cube, there's now two options. I can't color any of the first two. And then the last one, there's only one option. So that is going to be the number of ways we can color it. However, we've just said at the start, I spent a long time on this talking about it, that there's basically the setup isn't going to be, some of them are going to be the same. So imagine that I colored this one blue, um, but then if later on, if I colored number three blue, let's just go with it. Let's say blue, red, yellow, and white. If later on I did the second one red, and this one is yellow, and this one is white, see a different configuration according to this, then actually it would look the same, and you could get a third one here. So what I'm trying to say is we need to divide by three. We've triple counted the number of arrangements by doing 4 times 3 times 2 times 1. So the threes cancel. We're left by just doing 4 times 2 times 1, and there are 8 configurations. Okay, well done on your efforts on this question.